Okay, thanks, Ashley. Can everybody hear me? I did unmute myself, but want to make sure it's audible.
Yes, I can hear you,
Okay, great.
Leonid.
Saw a thumbs up and I hear confirmation, so I'll go on. I'm going to give a presentation today on some of our work to understand aerosol-cloud interactions in Northern Alaska. I'm going to focus on observationally based studies for this presentation. We're also doing some modeling work in this direction, but here I'm going to stick with the observations. And this is work that's been conducted predominantly by our research team at the University of Colorado and NOAA in Boulder, but also in collaboration with some folks from the national laboratories and the University of Oklahoma. And let me see if I can advance slides. Doesn't seem to want to, but there we go. Okay. So as many people here are likely aware, the physical and chemical properties of aerosol particles can have a significant impact on cloud properties through nucleation of hydrometeors. And this includes influences on things like cloud lifetime, precipitation intensity, cloud radiative forcing, and some of these things are illustrated by the figure on the right here, which is pulled directly from one of the IPCC reports. And the complexity of this problem is really been highlighted in the IPCC reports as leading to substantial uncertainty in understanding how aerosols and their influence on clouds impacts radiative forcing in the atmosphere and how that impacts climate. And so we want to understand further what sort of relationships exist between different aerosol particles and the resulting clouds that form upon them. And so while a lot of these studies have focused on warm phase clouds, here we're focusing on Arctic clouds, including both liquid phase and mixed phase clouds. And for the studies that I'm going to highlight here, we're really focused on addressing three central questions. The first is how local industrial pollution in Northern Alaska impacts properties of liquid containing clouds there. The second question is how aerosol loading appears to impact ice properties in mixed phase clouds. And then the third has to do with the extent to which we can use surface aerosol measurements for understanding aerosol cloud interactions at high latitudes. And that goes back to some of the stratification that we see in the Arctic atmosphere and how often there may be decoupling between the surface, the properties measured at the surface, and those relevant for cloud at cloud height. So jumping into the first question, how local industrial pollution impacts the properties of liquid clouds in Northern Alaska. For this, we used measurements from a DOE airborne campaign, the ACME 5 campaign, which was conducted with the DOE-G1 aircraft in the summer of 2015. It included 38 total research flights, so they were flying every few days. And the flight tracks from these different flights can be seen in the bottom left there, where the color coding is altitude. So you can see most of these flights were conducted at very low altitude between the surface and 2 kilometers or so. The exception to that is that there was regular profiling done at these different sites. So I'm using the mouse to point to a Liktok point here, Itayavik, Barbero, Tulik Lake, Ivituk, and Atkasuk. And so the aircraft would go to these waypoints and do profiles up to 6 kilometers or so. On the aircraft, we had a variety of instruments to measure aerosol and cloud properties. And this study is now published in ACP, it was conducted by a postdoc working with us, Max Mann. And so the first question, of course, is, well, what is the source of aerosol particles in the North Slope in terms of the anthropogenic particles? And here we're focusing mainly on the particles coming from the Prudhoe Bay area. For those of you familiar with this part of the world, you know that there's a lot of industrial activity here related to energy extraction activities. And that is illustrated here in the top left in the figure from Jesse Kremian's paper. And you see each of these dots here was a well site in the Prudhoe Bay area during the time of flight. And so if we look at aerosol measurements from the campaigns in the other 3 panels here, B, C, and D, you start to understand the magnitude of this footprint, let's say, from that Prudhoe Bay environment. here, each of these dots represents a point in space, and the size of the dot represents the number of samples taken at any of those points. And then the color coding represents different quantities. On the bottom left here in panel B, this is the smaller aerosol particles, seen as the difference between two condensation counters. On the top right, you see the concentration of larger particles, and on the bottom right, the refractory black carbon. And you can see in each of these, there's kind of a bullseye over that Prudhoe Bay area that shows up very clearly. And so we were interested in understanding what impact those particles might have on the cloud properties in the local environment. And so Max did a comparison of profiles at the different sites to look at relationships between, or just the cloud properties in general. And so here you're looking at histograms that illustrate the relationship between the cloud droplet effective radius on the horizontal axis and the liquid water content of the cloud. And of course, you would expect that as the liquid water content increases, you're also seeing larger droplets through the height of the cloud. But when you look at the different profiles on the left here from Kajvik, in the center from Licktock Point, and the right at Tulik, you see some distinct differences. The first is this tail of droplets occurring at larger droplet sizes and higher liquid water contents at the Barrow Observatory that you do not really see at a Licktock Point or Tulik Lake. The second thing that stands out is this higher occurrence of smaller droplets at higher liquid water contents. And so this is representative of a shift in the droplet size distribution occurring as the result of different aerosol particle populations with higher concentrations of particles over the Licktock and Tulik areas. Max used this information to calculate things like the collection growth rate of a droplet population, as well as the projected mean rain rate. These are illustrated here as ratios between Barrow and Licktock Point, where the Barrow site, because the ratios are greater than one, has higher collection growth rates and rain rates. This is the net impact of the observed droplet concentrations and size distributions on precipitation from these clouds. Shifting to the second question, how does aerosol loading impact ice properties in mixed phase clouds? Here we're using a different approach. This is a study conducted by a graduate student working with us, Matthew Norgren, which has been submitted to ACP, and he used a collection of radar data along with aerosol measurements from 8 years worth of observations at the North Slope of Alaska site, DOE operated facility and NOAA operated facility as well, to look at how ice water content through the atmosphere, illustrated by the green line here, changes under different aerosol regimes. And so he used a combination of radar data to look at the ice water content, or to retrieve the ice water content, surface aerosol measurements, and specifically he used the scattering coefficient here, and then thermodynamic properties from radiosondes to evaluate these relationships. So when he did this, he grouped the different cloud types by liquid water path to ensure that there weren't substantial differences resulting from just a different cloud type. And across the different liquid water path regimes, which range from essentially no liquid here in the top left to large amounts of liquid here, so it's steps 1, 2, 3, 4, 5. Across all of these regimes, he demonstrated that the polluted cases tend to have less ice than the clean cases do. And this is not only true in the ice water content retrieval space, but also in the reflectivity space. And this is somewhat different than what we might have expected. Initially, one of the hypotheses we had was that under polluted conditions, there would be more ice nuclei present in the atmosphere, and therefore we might expect to see more ice under those conditions. But here we see quite the opposite. And so one of the questions we have to ask is this simply an environmental factor? Are the environmental conditions under clean cases just different and therefore accommodating to having more ice present than clean conditions? So we tried to evaluate that using radiosonde measurements taken from the ARM site. And in that analysis, we essentially find that quite the opposite is true. You would expect that under colder conditions, you might expect to see more ice, or under conditions with higher ice relative humidities, you might expect to see more ice mass. And when you look at the comparison between polluted and clean cases, you see actually that the polluted cases tend to be slightly colder in general. And at least at the lower liquid water paths have higher ice relative humidities whereas at the higher ones, they're fairly equal. And so this doesn't seem to be the cause of these higher ice amounts in these clouds. So we tried to use other radar retrievals or radar measurements to obtain more information on the microphysics of the clouds. So here we're using the fall velocity as measured by the radar. And what you're seeing here now is the difference in the fall velocity through the height of the cloud. One thing I should have mentioned is that this height coordinate is normalized, so 0 is cloud base and 1 is cloud top. And so one thing that stands out clearly in the fall velocity is that there's a separation between the polluted clouds and the dashed lines and the clean clouds and the solid lines, with the polluted clouds having higher fall velocities across the board for the different liquid-containing clouds. And what this indicates to us is that you have larger particles forming at the top of that cloud because you see similar reflectivity values. That also means that you have a lower number of particles in that cloud top environment for polluted cases. The other thing you notice is that the growth rate through the cloud changes with liquid, and in all cases, the two polluted and clean get closer together towards cloud base. And so that indicates a change in the growth rate. And you can see that in the highest liquid water paths, you actually have a crossing of the two different lines. And this we interpret to be related to the riming rates in these clouds. So the accumulation of liquid droplets and freezing of liquid droplets onto ice crystals through the cloud column. And this makes sense actually, as when we look at a polluted case, tend to have smaller droplets, which are not collected as efficiently by the ice crystals falling through the cloud. And therefore you would expect the riming to be slower in a polluted case than you do in a fast case. So the third question that we tried to address is to what extent surface aerosol measurements are meaningful for understanding aerosol-cloud interactions. And here I'm showing figures from work done by Alison McComiskey that illustrates that when you look at in situ measurements of extinction at the surface in the green curves compared to the column aerosol optical depth, or retrieved aerosol optical depth, there tends to be an offset seasonally between these two. And this implies that the peak aerosol loading at the surface is occurring at a different time than that at aloft. And so you can see that here in the time series. You can also see it in the kind of monthly climatology shown below, where the peak in the column aerosol loading tends to occur later in the year, say April, May, versus the peak that's observed kind of February, March in the surface measurements. And so this seems to imply that we need to be very careful about how we conduct some of these studies, because if we're relying on surface aerosol measurements to indicate when conditions are polluted versus clean, they may not be polluted and clean at the cloud height. So to gather more information on this, we have been using measurements obtained from a tethered balloon system that's been operated by the DOE ARM program at Lake Point. And I'm showing here a photo of that balloon system being launched on the left and an example case on the right where we see very clear stratification in aerosol through the layer. So we have here 4 panels. The top one is relative humidity, is the color coding on the balloon flight track, which is shown by these dots here. The middle one here is temperature. One below it is particle concentration from an optical particle spectrometer, and the one below it is particle concentration from a CPC. Also shown in all these figures is cloud base from solometer in the orange dots, and then radar reflectivity in the gray color shading. And so you can see here we profiled from below the cloud up through precipitation, through the liquid part of the cloud, up to above cloud base, back down into the cloud, back above the top of the cloud, and then back down. And very clearly, you have some stratification occurring through the atmosphere, where we have an inversion, obviously at the top of the cloud, as well as some temperature structure below the cloud. But we also see very clearly that there's an elevated aerosol loading above the cloud layer here. While we're in the cloud, many of the particles are assumed to be activated, and therefore we see fairly low concentrations within that cloud layer and where the cloud layer has been. But this is an example of a source of aerosol particles that may be available to this cloud that we don't really measure at all at the surface. Here's another example, and this is one where we do not have nearly as much precipitation, but we still have these cloud layers as indicated by the ceilometer cloud bases here in these lines. And again, the panels are the same. Unfortunately, the relative humidity measurement was not working here, so please ignore the top panel. But for the other panels, what I want to focus on is, again, you see here the activated layer, low concentrations within this cloud deck, an elevated aerosol concentration above the cloud, especially for the larger particles, and then this this apparent accumulation of aerosol below the cloud layer. In this specific instance, we had a temperature inversion below the cloud layer, and so the cloud is decoupled from the surface, and you have just a slight transfer of aerosol particles to the subcloud layer. And so we're working to investigate these cases a little bit further and bring in a whole host of observations from the sites to understand better what's going on here in terms of the processing of aerosol by the cloud. So to summarize, we've illustrated that there are impacts on northern Alaskan clouds from local anthropogenic emissions. Such impacts could result in variability in cloud radiative properties and precipitation over a relatively small area. So these are regional effects that are occurring across the North Slope. Similarly, a long-term data set, through the use of a long-term data set, we've demonstrated that there are statistically significant differences in ice amounts in mixed phase clouds relative to the aerosol loading in the different types of conditions. And we indicate that such differences are consistent with different nucleation rates at the top of the cloud, as well as secondary processes such as those linked to riming at cloud top and throughout the cloud column. And then finally, the vertical structure of aerosol particles is very complex in the Arctic, and so observational studies to understand aerosol cloud interactions should try to take this into account to reduce noise in the signal that we're trying to establish, linking aerosol properties to cloud radiative forcing. So we're going to continue to conduct studies along these lines, and also, as I said earlier, integrate modeling work to better understand how the clouds and aerosols are interacting at these high latitudes. Just quickly, this work is supported mainly by the DOE Atmospheric System Research Program. Observations were conducted and obtained through the ARM program, and NOAA has also supplied funding for several of the investigators here working on this project. So I'll leave it at that and take any questions people may have. And it's quiet, so I either went way too fast, which is likely, or was very clear, which is unlikely. Or everybody's seen
it. Or we're all trapped on mute.
Possibility.
Gijs, this is Demal. I have a question about the ice nuclei impact.
Yeah.
Because those mid-phase clouds are generally low. Do you consider the impact of dynamic process for the ice nucleation or ice process in the cloud?
Sorry, do I consider
the dynamic process, like the boundary layer turbulent mixing?
Yeah, so we considered that indirectly by looking at the ice relative humidity, and admittedly only through a limited amount of radiosonde profiles, but we haven't necessarily looked directly at turbulence intensity as something to link back to these relationships. It would be interesting to think about doing that.
When you look at the aerosol impact, do you also look at the seasonal variations for those comparisons? I mean, previous study shows that during springtime at the Arctic, there's lots of dust events that could provide effective ice nuclei.
Yeah, I should have mentioned and didn't that we limited this study to the late winter and early spring, so it's not a year-round study. We were fairly consistent in the seasonality just to try to avoid strong differences in aerosol properties and types across the different seasons. But it's a good point that there are differences, and when we look at within our kind of subset of dates, the polluted and clean tend to be distributed fairly equally. So we're not seeing a strong signal transition time period, for example, where the second half of our time is clean and the first half is polluted. At least that's what I remember from Matt's plots on this.